Last night, you almost certainly dreamed. Sometime between falling asleep and waking, your brain constructed an experience vivid enough that part of you believed it completely. You have been doing that your whole life, and so has every human who ever lived. For roughly 300,000 years, in every shelter and cave and temporary campsite across the earth, people closed their eyes and entered a world their brains built entirely from within. They had no word for it, no framework for understanding it, but the experience itself was identical to yours. That strange, uncontrollable, hyper-realistic world the brain assembles the moment sleep begins. The biology underlying that experience has been stable for far longer than our species has existed. Dreams occur during REM sleep, a phase the brain cycles through several times each night, during which it becomes nearly as active as it is during full wakefulness. The eyes move behind closed lids. The body's muscles are temporarily paralyzed, and the brain generates an entire, internally consistent world from nothing. REM sleep is not a uniquely human phenomenon. It evolved in mammals tens of millions of years ago. By the time early hominids were moving across the African savanna 2 million years ago, their sleep architecture was functionally identical to ours. The same REM cycles, the same dream-producing neural systems, the same nightly experience of inhabiting a place that did not exist. The capacity for dreaming is not a recent development. It is ancient infrastructure. In 2000, Finnish neuroscientist Antti Revonsuo published a theory that substantially shifted how researchers think about the function of dreaming. He called it the threat simulation theory. His argument was that dreaming evolved not as a byproduct of sleep, not as random neural noise from a resting brain, but as a deliberate biological function, one in which the brain rehearses responses to danger before those situations are encountered in waking life. The evidence he drew on was notably consistent across cultures. The most commonly reported dream themes, in every population studied, involve being chased, falling, being attacked, losing teeth, and being trapped with no available exit. These scenarios appear in societies with no historical contact with one another, across different languages, geographies, and belief systems. The settings and characters change. The underlying threat structure does not. For early humans, this kind of rehearsal had direct survival value. A dream in which the dreamer was pursued by a predator, confronted by a rival group, or separated from camp in unfamiliar territory was, in functional terms, a low-cost simulation. The people whose brains ran those scenarios regularly were somewhat better prepared when the real version occurred. The fear response had already fired. Some form of a behavioral reaction was already encoded in the nervous system. A related line of research extends the timeline even further. In 2006, primatologist Lynn Isbell at UC Davis proposed that the human visual system co-evolved with snakes over millions of years in the African rainforest. The human eye is unusually efficient at detecting snake-like shapes, meaning long, curved, patterned objects obscured within visually complex backgrounds. This detection appears to occur faster than the recognition of faces or sudden movement. The visual cortex shows what appears to be a dedicated processing response to exactly this configuration of shapes. Snakes appear in human nightmares at a rate considerably out of proportion to the actual threat they represent in contemporary life. The visual system is still scanning for something that posed genuine, recurring danger to ancestors who predate the emergence of Homo sapiens by millions of years. That scanning does not stop when the eyes close. It continues during sleep, running searches calibrated for a world that no longer exists in the same form. Physical threat, however, accounts for only part of what the dreaming brain processes. A second major function identified by researchers is social simulation. Dreams are densely populated with other people, and the interactions within them, arguments, alliances, betrayals, reconciliations, carry the same emotional weight as comparable events in waking life. For humans living in small, interdependent groups of 20 to 50 people, social positioning was not merely a matter of comfort or status. It was directly tied to survival. Who trusted you determined whether you had allies in a crisis. Which alliances held determined access to food, protection, and cooperation. The brain had as much reason to rehearse those dynamics as it had to rehearse physical threats, and during sleep, it appears to have done exactly that, running social scenarios with the same regularity and intensity it applied to predator simulations. Memory consolidation represents a third identified function of REM sleep. During this phase, the hippocampus, which is the brain's primary memory processing structure, works intensively to consolidate the experiences accumulated during waking hours. Emotionally significant memories are processed with particular thoroughness. Matthew Walker, a sleep researcher at UC Berkeley who has spent decades studying this process, has described REM sleep as a form of overnight emotional regulation, in which the brain preserves the informational content of an experience while gradually reducing its raw emotional intensity. For early humans, this nightly consolidation had clear practical value. Navigation routes back to camp, plants observed to cause illness, locations where a specific predator had been recently active, changes in the behavior of group members that might signal coming conflict. All of it needed to be retained in a form that remained accessible and actionable. Dreams appear to have served, among other things, as the maintenance cycle that kept that information organized. There is also a line of physical evidence that may connect ancient, altered states of consciousness, including dream states, directly to material culture. The cave art at Chauvet in southern France, dated to approximately 36,000 years ago, contains recurring geometric forms alongside its more famous animal imagery. Spirals, grids, branching lines, and regular patterns of dots appear throughout the site. Nearly identical forms appear in ancient art on multiple other continents, across cultures with no documented contact with one another, and spanning tens of thousands of years of human image making. Archaeologist David Lewis Williams, who spent decades studying rock art across southern Africa and Europe, concluded that a substantial portion of ancient cave imagery was produced in altered states of consciousness, states that closely resemble the visual experience of dreaming and of the hypnagogic phase immediately preceding sleep. The geometric patterns he identified are known as entoptic phenomena. They are generated directly by the visual cortex, rather than perceived from the external world. Their consistent appearance across such a vast span of human history, on surfaces that ancient people returned to repeatedly over generations, suggests that some portion of what was experienced during sleep was later rendered on stone. One further body of evidence is relevant to understanding how ancient humans actually slept. A 2015 study published in Current Biology, led by Jerome Siegel at UCLA, tracked the sleep patterns of three contemporary hunter-gatherer societies: the Hadza of Tanzania, the San of Namibia, and the Tsimane of Bolivia. These groups live under conditions closer to prehistoric human norms than almost any other population on Earth. The findings showed average sleep durations of 6 to 7 hours per night, with sleep onset occurring well after sunset. Sleep timing was regulated primarily by the body's core temperature cycle through the night rather than by the presence or absence of light. This pattern likely represents how humans slept for most of their evolutionary history, which carries implications for how modern sleep disruption is understood. Some portion of what presents clinically as insomnia or irregular sleep timing may reflect the mismatch between an ancient biological system and an environment it was not shaped to operate within. What this body of research collectively describes is a picture that is both ancient and continuous. Early humans dreamed about the same broad categories of experience that populate modern dreams, not because their daily lives resembled modern life, but because the brain generating those dreams was structurally and functionally identical to the modern brain. The threat rehearsal, the social processing, the memory consolidation, the recurring geometric visual phenomena, none of it is recent in origin. None of it required language or settled civilization or any of the cognitive structures that conscious human life has since built around it. During sleep last night, the brain ran processes that were refined over millions of years of evolutionary pressure. It simulated threats, it worked through the social dynamics of the preceding day. It consolidated memory. It may have generated the same geometric visual patterns that people were painting onto cave walls 36,000 years ago. The program is old. It has not stopped running.